So let us review the last sessions and let us proceed further. And in the last sessions, we had seen the star configuration, and especially in the star configuration, let us say if we have a source, something like this. So source which is connected in star configuration, and one should understand in this star configuration one of the important like relationships are the phase and line quantities. So the phase voltages are the corresponding individual voltages, which are, let us say, ER phasor, EY phasor, and EB phasor. So these are the phase voltages of the generator. And if we see the lines which contribute to R phase, Y phase, and B phase are referred as the lines, and these lines are going to be connected to some load, in which the load can be either connected star or a delta. But anyhow, so let us think of that these are the lines of the generator from here to here, and the line which is connected to the R phase generator is called as R phase line. The line which is connected to Y phase generator is called as a Y phase line, and so on. Now, if we observe the voltage between R to Y, we call as line voltage as ERY. How do we get ERY is just simply write down the KVL we will get in this way. See, so start at the arrowhead of this ERY. So from here and reach to the other side through this path, like here Y phase, like we started at R phase line and we reached to the Y phase line. In the process, whatever we come across the voltages, you add up all those things, which are ER plus of minus EY. So like minus EY. So this is minus EY as because it is, and like we are coming across first non-arrowhead, then arrowhead. So like that you can find all other phase and line voltage relationship between these phase and line quantities. And one more interesting thing is that these currents, the currents which are flowing through these lines, we call as the line current. So this is R phase line current, this is Y phase line current, and this is B phase line current. So like that we will have the phase and line quantities relationship, and especially what I want to highlight is that the phase voltage is equal to line voltage divided by root 3 in case of star connected system, and phase current is equal to line current. Just try to get aware of these two important relationship in the star configuration. And one more thing is that the phase voltage, or you can say in another way that the line voltage leads the phase voltage by how much? 30 degrees. So these are the three important points, takeaway points out of this star configuration. Now let us see today the delta configuration and the phasor relationship between voltage currents of the phase and line voltages and phase and line currents. Okay. So first let me take the generator side, then let me proceed further that. So let us say, so here I have a three phase generator which are connected in delta fashion, as like this. So now you can say that this is a three phase generator, and whose system, let us say this is R phase corresponding thing, this is Y phase, this is B phase, and Just let me highlight that the voltage is also that this is E R2Y, that is R2Y phase voltage, and next is E Y2B phase voltage. This is E B yeah, E Y2B. So E Y B, and next is E B to R phase voltage. So these are the, see, try to observe in case of the delta connected system. In case of the delta connected system, you can see R phase line. These are the lines. I told you, just excluding the generator, other than generator, we call as a lines. So these are the lines. So now see R to Y, how much is the voltage? ERY, which is equal to this generator voltage. See, this particular generator voltage. That means in delta connected system, ERY, which is the line voltage, which is the line voltage, is equal to ER, which is the phase voltage. Phase voltage. So just quite opposite relationship as that of the star connected system. Here the line and phase voltages are same. Then what about the currents? So let us see that. So if this is the current flowing through the line, which is IR, and next is, so this is the current flowing through the line, which is IY, and next is, this is current flowing through the line, which is IB. These are what we call as a line currents. Now we can find these line currents provided if we know these individual generator currents. Like if this individual generator coil whose voltage is ERY is producing a current of I, let us say R Y, small case letters. Just I have some specific purpose for that. Just I am using small case letters for the current which are inside of this generator. And next is, so next is Y phase, so whose corresponding current is I Y B, I Y B, I Y B, and similarly one more current also there here. So this is I. So what we get? So BR, I BR. So let me say that these currents, let me write here that IRY comma IYB. Try to observe where are these currents. These currents are individual generator currents. So individual generator currents are generally called as a phase current. So IBR are referred as the phase currents. Phase currents. Now, if we know these phase currents, we can derive the line currents. So, for example, let I R Y is equal to some phase current magnitude IP at an angle of 0. Then once we know one of the phase current, we can write all other phase currents as like this. IYB is equal to IP at an angle of minus 120, and IBR is equal to IP phase current magnitudes, so minus 240 or plus 120. So these are the phase currents of the generator, individual phase currents of the generator. Once we know these phase currents, now we can derive the line currents. How? Line currents is equal to, how can we write line currents? Let me say R phase line current, this one IR. See, write down the KCL at this node. So here try to see IR and IBR is leaving. What is entering? IRY. So we can write IR as, so like simply what are the entering currents? Is entering currents is equal to leaving currents. So let me write here by looking at the diagram. So as like this, IR is leaving and IB are also leaving. What is entering? IRY. So this is one of the case. Next, at this node, so at Y node, so can I write in this way? IY is leaving, and what else is leaving? IRY. IRY is leaving. So what is entering at this node? IYB. So sum of the entering currents is equal to sum of the leaving currents. With that formulation, I am writing this. And next, IB at the B node at here. So IB capital B is equal to, what are the leaving currents? IB and IYB. So IYB is equal to entering currents IBR. So these are the relationship between line currents and phase currents. So let me bring that over here, and let me simplify this to get the line currents as IR is equal to IRY minus IBR. Next, from this, IY is equal to IYB minus IRY. And what about here? IB is equal to IBR minus IYB. These are the line currents. So now it is easy to get these line currents. How much are these line currents? Let us substitute IRY, IBR. So all phase current magnitudes are same. So which is IP and minus. So IP at an angle, IBR is IP at an angle minus 240. So how much we will get this? You simplify that. So this is IP into 1 at an angle 0 minus 1 at an angle minus 240. If you simplify this, we will get this as, so IP into root 3, or let me write root 3 IP at an angle of how much we will get this? I hope so it is 0 and 240, so I will get most probably 150. Just check it. Is that correct or not? Is that correct or not? 1 minus 1 at an angle of minus 240. Yeah, root 3 at an angle of minus 30 I got. Yeah, so if it is minus 30, then that also, just let me check if it is plus 120 instead of that, how much I will get. Yeah, so it is minus 30. I hope it's not 150, it is minus 30. Is my things correct? All of you got same answer or different answer? Yeah, it's minus 30 only, no issue. Similarly, so find these line currents. So IYB, how much is IYB? So IP at an angle of minus 120 and IRY is IP at an angle of 0. So how much we will get this? So 1 at an angle of minus 120 minus minus 1. How much is this? This is root 3 IP at an angle of minus 150. So for this, it will be lagging 120 degrees. You can cross verify. If you add minus 120, you will get this. Similarly, so IBR is IP at an angle of minus 240. And what about IYB? IP at an angle of minus 120. So how much you will get? Now it is easy to write. IP at an angle of minus 150 minus 120. How much you will get? 270 minus 270. Just check it. Suppose you should get minus 270 or plus some other value also correct. So in this way we can find the phase currents and line current relationship for a generator. And if we have so phase currents, like let me think of the phasor diagram form. If these are the phase currents, IR current is this one. So which is I, let me use same notation, RY, IRY, which is at 0 degree, IYB, is that IYB? Yeah. So IYB is at minus 120 degrees and IBR is at IBR is at plus 120 or minus 240. Both are same. Minus 240. Both are same. Now apart from that, how we get these line currents from these phase currents? Use the parallelogram law. Simple. Right? See what is IR? IRY minus IBR. Where I will get minus IBR? As like this. So take the negative of this blue color line, but opposite direction. This is what I B R, but negative. Now you add plus IBR with the negative value. So this minus IBR indirectly with the IRY. So how we add that? So draw the parallelogram and just take in parallel to the IRY one more line, and the diagonal of this will gives the line current, which is IR. How much is the angle of this? See, minus 30 degrees. Here observe carefully. So that's why I am getting this in downward direction. Similarly, you can find the other line currents. How? In the same way. What is IY line current? IYB, where is IYB? Here. Plus of minus IRY. So, minus IRY, where I will get? Opposite to the IRY. This is what? Minus IRY. Now you add this negative to the IYB current. Where is IYB? Here. So now if we add up these two currents by drawing the parallelogram as like this, then diagonal of this parallelogram will gives the resultant current, which is IY. How much is the angle of IY? Minus 150. So minus means clockwise. From where? From 0. From 0 this angle is 150. Carefully observe. I am keeping all the angles here. Carefully observe it. Similarly, IB. How I will get IB? IBR addition with minus IYB. So let me take minus IYB. This opposite to the IY is what? Minus IYB. Minus IYB. Small case letter. Minus, this is negative. Now you add up these by drawing the parallelogram, and the diagonal of this gives the line current, which is IY, not IY, it is IB. So in this way you can get all the phase and line current relationship, as because the phase voltage is equal to line voltage, you no need to worry much thing about the voltages in case of delta connection. But so the very important thing is that getting the line and phase current relationship in terms of even in the phasor diagram is very important. Okay. Now if you need the power, so power can be written as like this, like if I know this individual single phase generator is generating a power of something like voltage into current into cos theta, then three phase generator will generate 3 times of that value if it is balanced system. So let me write for balanced system, for balanced system, for balanced system, for balanced system. So the three phase power is equal to 3 times of P single phase power, which is equal to 3 times of what is the single phase power is? Single phase voltage magnitude into phase current magnitude. I might be used PH for the phase, is that? No, P only, right? And here, so phase voltage you can write VP or EP, it's your wish. So this is equal to EP phase voltage or VP. So either of the notation you can adapt. So now VP IP into cos theta. What is theta? Angle between voltage and current. This we seen previously. The active power and reactive power relationship. This can also be written as simply 3 times of the voltage current magnitude into cos theta, and which is equal to further that here try to observe the line current magnitude is equal to root 3 times of the phase current magnitude. Observe that. The takeaway point from here is that in the line currents, just try to observe. This is one line current and whose magnitude is root 3 times of IP. That what I am writing. IL means line current is equal to root 3 times of IP. So, which can be written mostly, so this kind of form will be remembered that phase current is equal to line current by root 3. In either way you can say, okay, both are same. But what about phase voltage? Phase voltage is equal to line voltage. Magnitudes, I am talking about only magnitudes. Angles may be different, but magnitudes are same. Now, if I use this relationship like IP is equal to IL by root 3 and VP is equal to VL, can I write this as VP is equal to VL for a delta connection and IP is equal to IL by root 3 for a delta connection. So, into cos theta, so this 3 phase power can also be represented as this 3 I can write root 3 into root 3. So, I will get root 3 VL IL cos theta. This is very important expression. So, that the 3 phase power can be written as 3 times of phase quantities or root 3 times of the line quantities. Both are correct. If you are considering line voltage, line current magnitudes in calculating the power, you should use root 3. If you are using phase voltage and phase current magnitudes, you can use only 3. Clear? So this is very important point, so that you should focus on it. And similarly, you can think of the reactive power also, 3 phase reactive power. So let me write Q 3 phase is equal to 3 times of Q single phase, which is equal to 3 times of single phase reactive power is Vp Ip into sin theta, which is equal to, now you can further write this as simply 3 Vp Ip sin theta, which can be further written that 3 times of Vp is equal to VL for delta connection, whereas Ip is equal to IL by root 3 for delta connection into sin theta. So for a delta connection, you can write the 3 phase power, reactive power as root 3 times of VL IL sin theta or simply 3 times of VP IP sin theta. Both are correct. So one more is the apparent power. S3 phase is equal to magnitude is equal to 3 times of S single phase magnitude, which is equal to 3 times of you can say VP IP. So which can also be expressed as 3 times of Vp is equal to VL for delta connection and Ip is equal to IL by root 3. So which can also be written as root 3 times of VL IL. So these relationship you try to observe carefully. Okay. Right. So now let us see the system that if the load is connected in delta. So let me say balanced delta connected load. Balanced delta connected load. Balanced delta connected load. Now almost same kind of relationship we see as like the source, but slight different. Just let me take the balanced load, delta connected load. So we stated what is balanced load, what is balanced source. One should understand that. So balanced load means each phase load impedance is the same. So this is what the load. Let us say this is R phase line, this is Y phase line, and this is B phase line. And now what I will say is that so R to Y I will call as I. Previously we used small case letters, so now I can use the same kind of thing, no issue. IRY is the phase current, and let me say this one as IYB is the phase current, and IBR is another phase current. And what about the impedances of these loads? The impedance of this load is Z at an angle theta. This also Z at an angle theta, and this also Z at an angle theta. All the phase magnitudes of the impedances are same and also angles are same, then it is called as a balancing load. And what about the line currents? The currents flowing through these lines are referred as the line currents IR, and this is IY, and this is IB. Now can we find these line currents in terms of the phase currents? So for which we need some additional thing, that just let me indicate that the voltages across each of these phases, like R to Y. So let me call as this voltage, phase voltage, as V, let us say RY. Next is VYB. Next is this phase voltage is VBR. These are the phase voltages. So let me write that. So the phase voltages of the system, let the phase voltages is equal to line voltages. So this is not assumption. In delta, let me write as like this. In delta, phase voltages is equal to line voltages. Now let those voltages as like this. If VRY is equal to VP at an angle 0, then what about next phase voltage or line voltage? By this time you should be in a position to write it. The magnitudes remain same. Angle will be minus 120 degree. Similarly, VBR is equal to VP at an angle of minus 240 or plus 120. Now observe that we know all phase voltages of these three phase load. Can we find its corresponding currents? As like this. See, IRY is equal to IRY is current through this Z at an angle theta. How much is its corresponding voltage? VRY. So VRY divided by Z at an angle theta. What is VRY? Vp at an angle 0 divided by Z at an angle theta. So this can be written as Vp by Z at an angle of minus theta. Similarly, you can write all other phase currents. What are they? IYB is equal to VYB by Z at an angle theta. So Vp at an angle minus 120. I'm sorry. Right. So this is Vp at an angle minus 120 divided by Z at an angle theta. Let me write all these things quickly. Vp by Z at an angle of minus 120 minus theta degree. Similarly, I BR, this current is equal to, its corresponding voltage is VBR divided by Z at an angle theta, which is equal to Vp at an angle minus 240 divided by Z at an angle theta, which is equal to Vp by Z at an angle of minus 240 minus theta. Once we know these phase currents, now it is easy to find the line currents. So tell me, what are the line currents as what we had seen previously? So can I say the entering currents is equal to leaving currents? What are the entering currents? IR and IBR are entering here at this node, at R junction here, and leaving current is IRY. For this triangle, delta connected triangle, one side, one edge is the node. So at this node, let us say N1. So the IR and IBR is entering, leaving current is IRY. So can I write IR is equal to IRY minus IBR? So let me write. So IR is equal to IRY minus IBR. We already know these phase currents here. You can substitute here and you can get the line currents. That is the way. Similarly, you can try the other currents IY. How can I write IY? See here. IY is equal to IYB minus IRY. IYB minus IRY. Similarly, IB, the phase current, line current of the B phase is equal to, let us see that how can I write IB. So IBR minus IYB. IBR minus IYB. So in this way you can get the line currents for the load also. So when we come across the load, the important thing what we need to look for is that what will be the phase voltages. Once phase voltages are known, now readily we can calculate the phase currents. Once phase currents are known, we can get the line currents. So if the load side information is given and if the source side information is given, so you can see as like in the above case. Okay. So now let us take one simple problem which demonstrate these things. So as let us say that, let me write the problem here. A that a balance a delta connected load, a delta connected load, a delta connected load, delta connected balanced load, balanced three phase load, of course, balanced three phase load is is supplied supplied from 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 a three phase from a three phase 400 volts supply, three phase 400 volts supply. The line current, the line current, the line current is 20 amperes. The line current is 20 amperes. So what we need to do is that find all the phase and line line quantities. Also find the phase impedance. So whenever you see three phase problems, the first most important thing is try to put the things into diagrammatic form. That makes your life simple. So what I will do here is that, see here carefully, or so let me take a delta connected balance load. What they said, delta connected balance three phase load. So first I will draw that load as like this. So let me take the delta configuration in this way. So just I will be assuming some impedances Z at an angle theta, as because it is a balanced load. So all phases have same equal impedances, and this also one more phase impedance which is equal to Z at an angle theta. So this is what the three phase load. Now what are we getting out of this three phase load is that this three phase load is getting power from the three phase source, and whose voltage is which voltage, they did not specified, but we should understand that from a three phase 400 volt supply. From this you should understand clearly that, let me draw that, this is something like R, so next is something like Y, and next is B. So these are like B phase corresponding thing, and Y phase corresponding thing, and R phase corresponding thing. So we call these corresponding currents as line currents IR, IB, IY. These are the line currents. These are the line currents. And they had given line current is 20 amperes. Which current they had given? Only magnitude is given. 20 amperes of line current magnitude is given. What else is known? Voltage is known. Which voltage? Tell me. Can you tell me? Three phase 400 volts means what does it mean? So generally the given voltage is usually the line voltage. Whenever it is not specified anything means it is the line voltage. But it is the delta connection. So I can say line voltage is equal to phase voltage since delta connection. Delta connection. Clear? Next is what else is given? That's all. Now we need to do lot of work. What is that? Tell me. So now I know line and phase voltage magnitudes are same. So can I say, as because it is a balanced system, now I can say V some notation as like this in the above. So you can use all these same notations, that RY, YB and BR notation, those things. So let me write this as V RY, and whose current is I R2Y. Next is V, this is B. So let me use that corresponding color. So this is V YB, whose current is I Y2B, I YB. And next is V B2R, whose corresponding phase current is I BR. Just as in the same, just if you do one or two problems, you will understand these things. So I hope, so this current direction is, yeah, so this current direction is correct, but here I should change the direction. This, yeah, so this current direction will be opposite. This current direction also opposite. For the load, wherever arrowhead is there, that side current should enter. So this is VBR. Now based on these things, just quite a simple task you need to perform that. Let me take all those things as it is. So here whatever uh, data I had, whatever I used in this derivation, I can take up similar to this derivation all calculations over here. See that? Now just let me put here and oh, jumping. Yeah. So now see here. Yeah. So let me just put beside these things. I'll come to that point. And here let me complete. How much is this? So line voltage is equal to phase voltage magnitudes. Both are same. VP is given. So you can directly write down straight away 400 at an angle 0. 400 at an angle of minus 120 and 400 at an angle of minus 240. These all are the phase voltages. Once you know the phase voltages, so you can see one more important point that what can we do is that just observe carefully here. Very important logic is there. Phase current magnitude is equal to phase voltage divided by let us say impedance magnitude. Let me write in this way that here IP is equal to IL by root 3, which is equal to 20 by root 3. But how can we write IL by root 3, which is IP, as VP by Z, VP by Z, VP by Z. So now we can get the Z magnitude. So how much is the Z magnitude? Now can you tell me? So as like this, Z is equal to VP divided by IP. So VP is equal to 400. IP is equal to IL by root 3, which is 20 by root 3. How much is this value? Let me check. So this is 20 by root 3 is 34.63 ohms. Is this correct? Is this correct? Alright. So this is the thing. Now if it is the resistive load, so we can proceed with the theta to be 0. If it is other than resistive load, some theta value will be there. So I am considering that, or let me say here itself. So the given load is load is resistive in nature. Resistive in nature. That means theta is equal to 0. So theta is equal to 0. Now you have every parameter. Voltage is there, impedance is there, impedance angle is there. You can find all the phase currents first. First let us do that task. Let me create some more space here to substitute all these values. And now let us substitute all these values. Just similar kind of derivation. Just initially it looked like little difficult, but as you proceed you will get in a simple way. The phase current is how much? 20 by root 3. How much is the phase current? So phase current is equal to 20 by root 3 is I got 11.55 amperes. So 20 by root 3. So directly I can write. So this is 11.55 at an angle 0. So this is also 11.55 at an angle minus 120. 11.55 at an angle minus 240. Then once you get this, you can get the line currents also in simple way, that root 3 times of phase current, magnitude also same like as it is, but there will be 30 degrees difference. So how that 30 degrees will be taken care is that the line current lags the phase current by 30 degrees. So 1 at an angle of minus 30 degrees. This thing you need to take care. Means if you want to write directly, you can just see. Let me show that corresponding calculation what we did somewhere. Where is that? Yeah, here see that. See, IP is at an angle of minus 30. When the corresponding IRY is at 0, this phase, this line current is lagging its corresponding phase current by 30 degrees. So if you remember this logic, directly you can write. You no need to do all these KCL equations. So, or you have to do substitution of these IRY and IBR. So IRY and IBR, you will get same value. So let me directly write. So root 3 times of IP is what the line current. So at an angle of minus 30, which is equal to, line current is already known. How much is that? 20 amperes. So which is root 3 times of IP is 20 at an angle minus 30 degrees. Similarly, you will get this as 20 at an angle minus 30 minus 120, which is equal to 20 at an angle minus 150. How I am writing directly? See this. So that is the advantage, that once you understand the basic idea of the delta connection, so especially for balanced system, it is easy to write all the phase currents, line currents and phase voltage, line voltages for all phases like R phase, Y phase, B phase. So I can write 20 at an angle of, so I can write minus 30 minus 240, which is equal to 20 at an angle of minus 270. So in this way, you can get all the line and phase quantities of the given delta configuration. Okay, thank you.